Hello and welcome back. Today we have 94 binary tree in order traversal. Given the root of a binary tree is a tree that has at most 2 children per node. We are to return the in order traversal of its nodes' values. So a quick review of the in order, pre-order, post-order. It's easy to think of it as you're incoming from some root. You're starting somewhere, and from there, if it's in order from left to right. So I'm here, I'm always starting at some root. I can point elsewhere, but from here, I want to add my right. Let's say my right is, my left to right in order. So we're going to add the 2, then we add ourselves, which is a 1, then we add what's to our right, which is 3. If it was pre-order, because I'm starting from my location, I put myself first, so I go first, and then I add my left and my right. If it was post-order, I'm starting from myself, but I want to add my children first, so I add my left child first, then my right child, then only after adding both my children, then I add myself. Okay, so if we move on to the actual problem, I added this as an example we can go through. So once again, in order traversal is left to right, where I add my left child, then I add myself, I'm in the middle, then I add my right side. Okay, so if we go through this example, and one of the caveats is it does say the recursive solution is trivial. Can we do it iteratively? And I realize they're actually very similar in logic. So what we cover here will cover both approaches, and we can go through both as well. Okay? So first thing we need is we want to ultimately return some list of values. So let's initialize that to an empty array, which will fill with our values in order. We also have a stack. We have a stack so that we can add and pop off from the back. Okay, let's move this guy a little this way. All right, now remember left, self, right. So whatever the case, we're always starting from ourself. But because we're going in order, where we want to go left to right, left middle, I'm in the middle, and then right, we keep adding what's to the left of us. Okay, to the left I have a 2. All right, let me add the 2, right? Let me add the 2. Then I keep adding. 5 is to the left of 2, so I add my 5. And then here, there's actually nothing to the left of 5, so that's okay. So once there's no more left, I add myself. So let me add myself. Let me first take myself off the equation. Let me add my own value. Once I add myself, left, self, right. Once I add myself, I need to process my right. So let's set the pointer back to 6 at my right. And then always check the left. So I'm on 6, but I care about its left. I'm 6 now. There's nothing to my left. So I add my value, and I try to process my right, but there's nothing to my right. Cool. So these two are done. We jump back all the way up to here. From this stack, we pop off whatever's next in stack. So let's remove that. By the time we get here, it means that there's nothing left on the left side. Everything on the left has already been processed down here. So, okay, so now I add myself, I'm in the middle, and I want to process what's on my right, but there's nothing there, so that's all right. 2 is done, and then I should have added 4 to begin with. 4 was the first one. 4, then 2, then 5, then 6. So now I'm on 4. Okay, so this is done. I'm on 4 again, which means everything to the left of 4 has been processed. And now I want to add or process my right side. My right side is an 8. I always want to process left, middle, right, so there's nothing on the left. So I can add myself to the stack, and I set root to 9. I add 9 to the stack. Oh, you're getting messy. Okay, now I added, I'm 9 now. Now I'm 9. And I want to process my left first. So, okay, I add the 1. And then I want to process my left, but there's nothing on the left. So now it's my turn. My turn to get added to the results. And once I add myself, I want to add the right. So let's add the right. And remember, we still have 9 and a 10. Okay, so on my right, now I'm 10. I am 10. I want my left process, but there's nothing there, so now it's my turn. I'm in the middle, so let me add myself, and then I care about what's on my right, but there's nothing there, so this one's done too. So the only one remaining is a 9. So by the time I get off this stack, it means everything to my left has been processed. So now it's my turn. I get to go into results, and I can now try to process my right. My left is already done. It was my turn. My turn is used up. I go to my right. Nothing there. So this is our result. 5, 6, 2, 4, 8, 1, 10, 9, 1, 10, 9. Let's see. So, 1, 10, 9. So if we visualize this, it's pretty much what we had here. That way, this way, that way, this way, and the result that we have is, if we copy it here, and that, it's 5, 6, 2, 4, 8, 1, 10, 9. Okay? And so that checks out. All right, so how do we convert this to code? Well, we can actually, what did we do here? All we did was we always started from wherever we were coming from, and we always come from the root. And I care about my left side, so I become the left. Okay? I become the left, and I keep going until there's no more left. Only when there's no more left, then it's my turn to get added, and then I care about my right side. Okay? And whenever I'm in a new node, I always care about my left. Only after the left is all done, then it's my turn. Then I go to the right. And this is the logic that we follow through. So let's do this here. Okay. So let's do what we did, but in code. We have a result, and we have a stack. And we're doing something while true. What we're doing is saying while there is a root, we want to append the root. So we always start from here. Unlike this guy, we remember to add the root first. Then we move to our left. And there is a point when we exit or exhaust our left side. If there's no more to process, then we're done and we can return the result as is. Otherwise, we take whatever's next in our stack from the right, from the end more so, and that means it's our turn. Once we exit here, we process everything on the left. There is no more left, so we add ourselves to the result, or our value, and then we're going to move to our right. Root is equal to node dot right. Okay, and then we should be able to run. All right, once again, our special test case was this guy right here, kind of a very zigzaggy test case. And then we submit, and there you have it. That's once again 94 binary tree in order traversal, where we start on our root, exhaust our left side, then it's our turn, then go to the right side. But after we go to the right side, we again exhaust the left side, then it's our turn, go to the right side, and so on. Thanks so much. Happy coding. See you next time. So I thought I'd go over the recursive solution as well. I'm sure it's pretty standard right now, but so we can have a DFS function, and I really want to do this just to show that it's very similar in logic. So what we did here, we're coming in from some node value, that's our root. And first of all, if not node, then we're done, return. Otherwise, for in order, we want to process the left side, so all we do is call DFS on our left. Then only can we add ourselves to our result. Result.append, node.val. Let's make sure to initialize our results. And we're going to call our DFS with our root and ultimately return res. Okay. And then we process our right side. So the logic is very similar. We always are incoming from some node. That's our root. We're incoming from here. We exhaust the left. We add ourselves. We're the middle. Then we move to the right, where this will now be the incoming node and will exhaust its left, then add itself, then jump to the right. And yeah, that's it. Thanks so much. Bye again.